Hi, everyone, and welcome to the wonderful world of population growth and size. In this video, we're going to be looking at how population growth and size interact with the population itself and also with the population also with the environment that the population exists in. So, how many humans are there on Earth? You probably know this number. We just reached it last year. We have 7 billion humans on Earth. A little over 7 billion now. It's like 7.05 billion. And as you can see, our population curve is looking a little bit scary. When we, earlier on, we had a pretty uneventful population growth until we hit about the year 1600. When we hit 1600, we started seeing this really extreme uphill trend that, funny, is in the shape of a J. So what do we call this? We call this a J-shaped curve. And a J-shaped curve is the way a graph looks of a population that is experiencing exponential growth. The population is growing exponentially. And it's growing as if there are unlimited resources. There is unlimited space. We have an unlimited amount of food to eat, air to breathe, clean water, and we don't really have much competition either. And we don't have competition from predators, and neither do we have competition within ourselves. So you can say that our human population is acting like this thing called biotic potential exists. And biotic potential is basically Biotic potential is basically the maximum growth rate of a population given unlimited resources, unlimited space, and lack of competition from predators. And this is what we're seeing with the human population. We are in biotic potential. We are pretending that there is unlimited resources. Let's look at a different, more ideal population growth curve. This population curve is called logistic growth. And as you can see on this curve, we do see a bit of a J shape. But then it begins to flatten and cap out on this magical dotted line known as the carrying capacity. And the carrying capacity, you'll want to write this down, is the maximum number of individuals that a population can sustain given a certain environment. I like to compare the two carrying capacities of a desert and the rainforest. The carrying capacity of a desert is going to be much lower. There is much less life that can be supported there, and that has a lot to do with its abiotic factors. There's not a lot of water, the temperatures are pretty gnarly and extreme. Though we have a great diversity of life in the desert, the abundance of life or the biomass of life is pretty low. If we look at the rainforest, you can see that if you've ever been in a rainforest, you know that a trail doesn't exist in the rainforest. It gets grown over within 2 days. So when we were in Costa Rica, everybody carried a machete. And everywhere they walked, they were just cutting down vines and making sure that the paths stayed clear for places to walk. So we know that the rainforest has a really high carrying capacity. It can support a lot of life because it has high rainfall and it gets a lot of energy from the sun because it's directly at the equator, which means that it can grow a lot more plants, which means that there can be a lot more animals that eat those plants, which means there can be a lot more animals that eat those animals that eat those plants. So the rainforest, biotically, has a much greater carrying capacity than the desert. So in a logistical growth, we see this trend, this kind of scary upward trend that we're experiencing right now, and a level off right at the carrying capacity. Now, this would be would be pretty ideal for us. Ecologists estimate that Earth's capacity for humans is about 12 billion. We're at about 7 billion now and really quickly approaching that 12 billion mark. So hopefully we can get our population to level out before we reach a pretty destitute situation, which I'll talk about a little later. Now, when we talk about carrying capacity and we look at biotic potential, basically growth with unlimited resources, then why don't we see herds of animals everywhere? Why, when you're driving down Highway 5, that wonderful straight stretch of highway in the beautiful Central Valley of California, do you not see tons and tons of birds and herds of animals everywhere and bugs? And, well, you do see a lot of bugs. But how come we don't see the earth just crawling and carpeted in life? Well, that's because there are things called limiting factors. And these are things that control population size. And we have them separated into two different categories. We have density dependent factors, which I abbreviate as DD, just for note's sake. And density dependent factors are exactly what they sound like. These factors come into play depending on the density of the population. So these are things like, we get a different color here. There we go. These are things like food supplies, habitat, waste buildup, these are things that come into play, that become an issue when a population gets more dense. So if a population is growing and exceeding its food supply, then you're going to see a decrease in that population as you see competition within the members of that population. Density independent factors are pretty much the opposite. These are limiting factors that are caused by something other than the amount of people or the amount of individuals competing for basic survival resources. These factors, I group them into simply natural disasters. And this can be flood, drought, hurricanes, earthquakes, tsunami, etc. These are things that happen to both the humans and animals and bacteria. These are things that limit the population, that are basically out of our control and have nothing to do with the size of the population or the density of the population. Therefore, it's density independent. And now I have a few examples of these and we can go through them so we can get a good idea of what's density dependent and what's density independent. So here is a picture of a slum in Pakistan, and slums are highly densely populated areas, and they're usually centered around some sort of natural resource. Here they're centered around a waterway, and they're usually outside of the main city hub. So this is a slum called Lahan, and it's right outside of a main city in Pakistan. And you could see these houses, how in close proximity these people live, and their close proximity to their water source, which is a basic human need, right? Which this water source now is pretty polluted. But within this situation, you have direct competition for space. You have direct competition for resources, such as being near the water. And in a situation like this, if there were to be some sort of disease or some sort of bacteria, it would spread incredibly quick because these people live so close to each other. It'd be really easy to have a very, very quick and fast-moving epidemic. I would call this density dependent. Now, if we look over here, we see a cheetah with a gazelle, and in the savanna, it's kind of incredible to think about the savanna ecosystem. The basis of the ecosystem is the grassland. This is just billions of pounds and tons of grass that is just growing and is just so excited to be eaten by herbivores, grass eaters. So if you have a ton of grass and then you'll have a ton of grass eaters. And the grass eaters are all sorts of gazelle and hoofed animals. And if you have a ton of grass eaters and herbivores, you're going to attract some gnarly carnivores that want to eat those herbivores. So within a savanna ecosystem, we see that the amount of grass gives rise to a certain amount of herbivores, which gives rise to a certain amount of carnivores. And I would call this density dependent. Now let's look at these two. This is a hard picture to look at, but I put this to represent famine. And actually, there was a famine that occurred in 1770, and it is the single most deadly, they're calling it a natural disaster that the world has experienced. Over 10 million people perished. And what happened this is called the Bengal famine. Famine. And it took place in India. And what happened were several consecutive years of drought, along with some government issues and war. But there was the drought, basically, the population went through its stored food supplies and wasn't able to replenish. And so within a year of the drought, people were dying of starvation. And this claimed nearly 1/3 of the population in that area, which is huge. So I would call this a density independent factor, as it was caused by drought. This picture, you guys might remember this. It occurred in 2004. This is probably our most recent pretty large natural disaster. It's actually number seven in terms of death toll in human history that we have record of. And this is the Indian Ocean tsunami. And I remember when this happened. It happened on December 26th, 2004. I saw it on TV and I couldn't believe my eyes. But this claimed the lives of 300,000 people in the neighboring countries around the Indian Ocean that were affected by it. So this is a natural disaster. It would be considered a density independent factor, right? The tsunami wasn't like, oh, there's a lot of people that live here, so I'm going to aim for this area. No, there is no pattern well, there was a pattern, but in terms of how dense the population was, it didn't matter. It affected uninhabited coasts, and it affected coasts with large cities on them. All the same, it was a density independent limiting factor. Now, we're going to take a look at population cycle and kind of put together what we know of carrying capacity and biotic potential and also limiting factors. So I'm going to create a little graph here. And if this is number of individuals, I'm going to just say N. And if this is time, right here. And I'm going to do a little dotted line. And this little dotted line is going to be our carrying capacity. Carrying capacity is often signified by a K, just so you know. And let's use green for our population. Well, we can see that human population, and this happens with a lot of other different species, is experiencing that exponential growth. There we go. So it's exponential growth. We're growing and growing and growing until we reach our carrying capacity. And what happens is we actually go a little bit over our carrying capacity because it takes a while for those density dependent factors, limiting factors, to kind of kick in. We have reached our carrying capacity. Now there's intra-specific competition, which means competition within the same species for things like food, habitat, other resources crucial for survival. So the competition gets thick, shall I say. And we have this, it takes a while for those limiting factors to actually become limiting. So we call this a population overshoot. And once the competition ends and we have our winners and our losers, we start to see a collapse. And this collapse occurs because there's simply a population cannot be sustained above a carrying capacity. It simply can't. So it has to collapse. It has to decrease at a point in which it's going to be more sustainable. So it usually, just like we had this kind of lingering effect of the overshoot, the collapse has a lingering effect as well, and the population will actually dip below the carrying capacity. And it'll hang out there for a while. And since it's below the carrying capacity, people are stoked. They're like, I got all the food I could need. I have an awesome, huge house. I'm super excited to be alive. And so what happens is they're like, since life is so great, I'm going to have all sorts of babies. And so we see this increase again, like a little mini J-shaped curve. And what happens is our population goes through this cycle of overshoot and collapse, where we're constantly growing and surpassing that carrying capacity. And because that population cannot be sustained, we have this massive die-off that dips us below the carrying capacity. And since it takes a little bit of time for resources to replenish, we have a little time where we're below the carrying capacity, and when those resources do replenish, our population grows. And what can happen is, I don't know about you, but this kind of doesn't seem ideal. I don't really like the idea of this collapse thing happening often. I don't like the idea of having mass amount of humans die, such as what happened in the Bengal famine. So we're going to take a look at the more details of this overshoot and collapse and where it's going to happen geographically. But another thing that comes into play is the idea of some sort of mega environmental change. And this can be anything. It can be, some permanent environmental damage like global climate change, or a depletion of a really, really important resource like fresh water. And what's going to happen is that's going to establish a new carrying capacity. Because the environment became damaged to a point where it can't be repaired, our carrying capacity is going to decrease. And when it decreases, our collapse is going to keep collapsing until it is well below that new carrying capacity. And then the roller coaster ride of overshoot and collapse continues around that carrying capacity. So that is population cycle. Let's review a little bit at the video. In this video, we learned about biotic potential, which is basically the rate at which a population will grow given unlimited everything, food, habitat, everything. And then we realize that, well, that's not really a really realistic situation, and that the world does have finite resources, and we do have this thing called carrying capacity, which is the amount of the population or individuals that a specific area can sustain. And that carrying capacity is reached when we start to see, little alarm, when we start to see these little limiting factors cap that population right at the carrying capacity. These limiting factors include density-dependent factors, which have to do with the density of the population, and density-independent factors, which have nothing to do with the density of population and typically are natural disasters. Then we looked at exponential and logistic growth. Logistic growth would be a little more ideal if we realized our carrying capacity and sustained ourselves below it. And exponential growth is what humans are experiencing, and that's when we have that population cycle of overshoot and collapse, which seems like a very volatile, very sad world. Anyway, I wish I had something pleasant to leave you with. How about my hat? Yeah, Christmas, Merry Christmas, holly jolly, ho ho ho. And with that, that's all, folks. I hope you enjoyed the podcast and have a great day.